So we have seen how to compute the longest common subword and the longest common subsequence between a pair of strings. So let's look at a very related problem, that of computing what is called the edit distance. So supposing I have two sentences, so in general these could be two larger pieces of text, an entire document, which read as follows. So the first one says, the students were able to appreciate the concept optimal substructure property and its use in designing algorithms. Second says, the lecture taught the students to appreciate how the concept of optimal substructures can be used in designing algorithms. Now clearly these are similar sentences, and one could imagine that the second sentence was perhaps created by editing the first one. So the question is, what does it mean to edit a document? So our goal is to try and find out how much editing was done, or what is the minimum amount of editing needed to make the first document look like the second document. In this case, a document is just a sentence. So what do we mean by edit? Well, you can insert a character, or you can delete a character, or you can replace one character by another character. So every operation applies to one character at a time, one symbol at a time. Either you can insert a symbol, delete a symbol, or modify one symbol by replacing it by another one, which we call substitution. So if you have used word processing tools, then sometimes they have this way in which you can track changes. So if you would track changes, then it will show you what are all the insertions and deletions that you have done, so that you can reconstruct what has been done to the document after editing. So here, for instance, we have shown in green underline what happens when we go from, so we are going from this document to this document, right? So here it says the students, and here the and students is separated by this section. So we insert the words lecture taught the. So if we insert the words lecture taught the, then we get the lecture taught the students. Now we come to this part. So it says were able. Now here we don't have were able, we just directly go from students to appreciate. So we delete were able here. So in this way, step by step, we can take the first sentence and appropriately modify it to get the second sentence. So the three different types of modifications, as we said, one is to insert a character, the other is to delete a character, and the third is to substitute. So here, for instance, we started with ITS and we wanted to go to B. Now there are many ways to do this. You can delete all three characters and then insert B. But here what we have chosen to do is to delete the I and then replace the T by a B and the S by an E. So we have done two substitutions instead of three deletions and two insertions. So you can think of it as saying that instead of doing 5 operations, 3 deletions and 2 insertions, I have done 3 operations, 1 deletion and 2 substitutions. So we are assuming that each of these has the same cost. Whether you delete a character or you insert a character or you substitute a character, you are paying the same cost in terms of the editing cost. So one thing to keep in mind is that we are only looking at the non-blank letters. So technically speaking, you would also be inserting these spaces here and deleting spaces and so on. So we have not taken that into account in this calculation. In a more careful calculation, you would also keep that in mind. So here we are only talking about the visible characters in this particular example. So we are interested in how much time it takes, or what is the cost of going from one document to another document, and this is what is called the edit distance. So the edit distance is just the number of edit operations that you need to go from here to there, right? And in particular, since there are multiple ways, as we saw when we looked at the example of transforming ITS to BE, there are many ways to do the same thing, and they may all have different costs in terms of number of operations. So we are typically interested in the minimum cost. So this is like the shortest path in a graph. Here we are looking for the minimum edit distance, the minimum number of changes I need to make in terms of these 3 operations to go from one document to another. So if we count what we have done above and you look at it carefully, then you will find that there are 24 new characters which were inserted in going from the first sentence to the second sentence. 18 were deleted and 2, the ones in ITS, the T and the S, were substituted. So in our case, this particular way of doing it, we have incurred a cost of 44. So remember that the edit distance is the minimum over all possible ways of doing it. This is one particular way in which we have done it. It need not be the minimum, but we certainly know that the minimum cannot be bigger than this, right? So we can do it definitely in 44 operations. So the edit distance is at most 44. Perhaps there is a clever way of doing this. So our goal, of course, is try to compute this edit distance efficiently. So this edit distance is often called, is more properly called the Levenshtein distance, because there are multiple actually ways of defining what it means to edit depending on what operations you allow. So the Levenshtein distance was discovered or invented by Vladimir Levenshtein in 1965. And why would we use edit distance? Well, imagine that you have mistyped something in a word processor or on a web page. Then sometimes you get a correction suggestion. So how do you suggest corrections for a misspelled word? Well, you look for the nearest word. So you assume that the misspelling has occurred because of some key or keys being mistyped by the person using the keyboard. So if you can compute the shortest distance words in terms of edit operations to the word that has been typed which is unfamiliar, then you can suggest a list of familiar words which are close enough and which are likely to be the ones that the person wanted to type, right? So spelling correction is one natural thing. And last time we looked at this least common subsequence, longest common subsequence, as one measure of genetic similarity. Well, you can also think of the edit distance as a measure of similarity between two documents and therefore two strings of any type. So if I look at the genetic code as a string and I ask how many genes must I alter to go from one species to another species, then you get some measure of how close the species are biologically. So the longest common subsequence is clearly closely related to this problem, because that also measures somehow how much two strings overlap. So if you look at the longest common subsequence, what it says is that there are, so supposing there are m letters in U and there are n letters in V, and supposing the LCS, the length of the longest common subsequence turns out to be k. That means that I can find k positions which are aligned in some sense. If I skip the gaps, then these k positions appear in the same sequence in U and in V. So how many things are not there in this sequence? Well, in the first string there are m minus k, right? And in the second string there are n minus k. So the more that k is, the less that m minus k is, and the less that n minus k is. So the longest common subsequence also corresponds to the minimum number of edits which I can perform by just deleting. So if my only edit allowed is to delete from one of the two strings, then in that process I can edit the string down to the longest common subsequence with the minimum number of deletes. Now deleting from one string can be equivalently replaced by inserting in the other string. So let's look at one of the examples that we saw last time. So if we look at the strings bisect and secret, then we said that the longest common subsequence is actually SCCT, which is SC with a gap and T in the second string. So how do we get from these two strings to this longest common subsequence? Well, the natural way is to delete these letters which don't appear. So I can delete the B and the I in bisect, and I can delete the R and the E in secret. But equivalently, I can get down to the longest common subsequence from one string and then reconstruct the other string by insertion. So for instance, I can start with bisect and delete these two strings, and then inside this I can insert, instead of deleting from the other one, I can insert in this one. So there is a symmetry between inserting in one string and deleting in the other string. So it becomes a little simpler to think of it this way, because now I can focus on only one string. So like what we did with the document in the previous example, we started with the first sentence and we edited it down to the second sentence. Now in principle, editing allows you to edit both ends, because you have two, the source and the target, and you might ask, well, can I change something in the source to make it closer to the target? Can I change something in the target to make it something closer to the source? Now as far as inserts and deletes are concerned, what we see is that they are symmetric. Right? If you insert in one, it's deleting in the other. If you delete in one, it's inserting in the other. So you can make all your edits in one source and you will count the same. What about substitution? Well, substitution clearly is symmetric. If I replace an A by a B going from here to there, it's the same as replacing a B by an A going from there to here. So therefore, it's enough to focus in editing in one direction. And in particular, this LCS is equivalent to edit distance without substitution, because deleting in both strings is the same as inserting and deleting in one of the two strings. So let's look at how we would discover some inductive structure for this problem. So as before, we assume that U is of length m, so it is a sequence of letters A0 to AM minus 1, and V is of length n, so it is B0 to Bn minus 1. So remember our LCS inductive definition. We said that we look at the LCS starting from AI and starting from Bj. So we call this LCS I comma j. And what we said was that if those two positions overlap, that is a of a sub I is equal to b sub j. The letter at the ith position in A in U is the same as the letter in the jth position in V. Then without loss of generality, we can include that letter in our longest common subsequence and then continue to find the longest common subsequence to its right. So we start at ai plus 1 and bj plus 1. On the other hand, if they are not equal, then we said that we have this situation where you have ai and bj and we don't know which one. We know that both cannot be in the sequence, because if this is matched with something, then we said that this cannot be matched with anything else because it has to be to the right of ai. So only one of them can be there. We don't know which one. So what we do is we construct this subproblem which has ai but does not have bj. So we take I comma j plus 1, and we have the other subproblem which has bj but not ai. So is the problem which is of the form I comma j plus 1. And then we look at the longest common subsequence in these two problems, and then we take the maximum. Right? So this is not like a greedy strategy where we decide arbitrarily that one of the two is going to be better. We say we don't know which is better, so we will exhaustively try both and then take the maximum. So this is how the LCS works. So let's see how edit distance works. It should be similar because we have seen that edit distance is not very different conceptually from LCS. So remember that we have said that inserts in one string are equivalent to deletes in another string. So rather than looking like some bidirectional deletes, we can assume that we are starting with u and transforming it to v. So all our changes are happening only in u. So first, if ai is equal to bj, then I can just proceed with the edit distance of the remaining strings. Right? There is nothing to be done because at this point the two strings are equal. On the other hand, if ai is not equal to bj, then instead of LCS I had two options, right? I could drop ai or drop bj, but now I'm transforming. So how do I make ai equal to bj? Okay, there are three ways I can do this. The first is that I can just directly replace, right? I can say make ai bj by just replacing it. I substitute ai by bj. But this is not the only option, right? So I have ai plus 1, and then I have bj plus 1, right? So the first option is to just take this letter and replace it by this letter. Okay. Another option is to delete the ai. So I have ai plus 1, bj plus 1, right? I just remove this and then I proceed, because I know that if I don't substitute it, then that there is a mismatch. So I must make it equal, and one way to make it equal is to remove the offending letter from that string, or I can insert. Remember, I'm making all my changes in u. So the letter ai does not appear at the beginning of the string that I'm looking at in B, so I delete it, or I make bj appear by pushing it up. So I put it as bj, ai and so on, and now in the second string is bj and so on. So then I know that this bj and this bj match. So now it's enough to look at ai and bj plus 1 onwards. Right? So there are these three options that I can do. Right? So if I look at this, then this gives me a natural recurrence. It tells that if I look at the edit distance from ai and bj, ed of I comma j, then if ai is equal to bj, I have nothing to do. The edit distance of I comma j is the same as the edit distance from I plus 1 and j plus 1. On the other hand, if it is not the same, then I have to make one edit to rectify this problem. So that one edit could be a substitute, right? If I substitute, then ai and bj are now correctly equal to each other. So I go back to the earlier case and I just look at the remaining string. So it's 1 plus the edit distance of I plus 1, j plus 1. On the other hand, if I delete ai, then effectively I have started with a new string starting from ai plus 1, but the other string still starts from bj. So then I'm looking at the edit distance from I plus 1 and j. And finally, if I insert bj here, as we said, then we are actually deleting this thing. So we have inserted bj before ai, so ai is still there, but bj now has been matched up. So I can look at the string from bj onwards and think of this problem as I comma j plus 1. So I have now three options. I don't know which one is best. I'm looking for the minimum edit distance rather than the maximum LCS. So I take the minimum of these three costs and then add the unit cost for the edit operation which I was forced to do at this step. So this is now our recurrence for the edit distance. Now as usual, we allow the two strings to go off so that both of them become empty. So we go beyond the last index n minus 1. Then the edit distance when we are beyond the last index in both is 0. right, because both have become the empty string. If I look at the string starting at position n in m in u and n in v, I get the empty string. Now what we said in the longest common subsequences is one of them is exhausted, then the other one, all those positions are also 0, but here it's slightly different. So if I look at the edit distance of ai to an minus 1 compared to the empty string, right, this edit distance is not 0. The longest common subsequence is 0, but how do I edit the first string to get there? Well, I delete all of this, right? So I delete all of this and come here, and how many things do I have to delete? Well, there are I things before this, a0 to a minus I. So I have to delete m minus I things, because I things are already missing. M minus I letters are still there in my string. I need to delete all those m minus I letters. So if I look at the edit distance from position I in the first string, and I've gone to the empty string in the second string, then the edit distance actually m minus I, corresponding to deleting this entire suffix from I onwards. And symmetrically, right, if I have the first string empty and the second string starts at bj, then remember I'm always operating on the first string. So instead of deleting from the second string, I'll think of it as inserting into the first string. So I insert the suffix starting from bj into the first string to make them equal. Again, I have to insert j minus n minus j things, right, because from 0 to j minus 1 are j letters which are missing out of n. So n minus j letters remain, and those letters must all be transported from v into u. So this now sets up our recurrence fully. So we have this base case. So actually you can get these two cases by just expanding the base case and looking at the inductive thing, but it's useful to just think of these as boundary conditions, because notice that one of the two cases will not appear, because I cannot go to I plus 1 and j plus 1 because I'm already at the end of one of the two strings. So with these base cases and that inductive definition, we can now set up our problem, right? So our subproblems are of the form ed I comma j for every I and j from 0 to n and 0 to m. So I from 0 to m, j from 0 to n. And as before, we will set this up in our two-dimensional matrix of size m plus 1 times n plus 1, right? So our same example, bisect, which is of length 6, and secret, which is of length 6. So we have the 7 by 7 matrix with entries, all the rows and columns labeled 0 to 6. And like in the edit distance, like in the LCS case, the dependency is basically looking at the three neighbors to the right, diagonally to the bottom on the right and right below, right? Because the edit distance I comma j, depending on whether it is equal or not equal. If it is equal, then it is just the value at I plus 1, j plus 1. If it is not equal, I have the three cases, right? I have the substitute case, which takes me to I plus 1, j plus 1. Or I have the delete and insert case, which will take me to ij plus 1 or I plus 1j, depending on which one it is. So I have the same dependency, and as before, this value is the one where I don't have anything on the dependent side, right? So for m comma n, I can start by initializing it to 0, and this was the boundary case that we said that if I now take, if I keep n as 6, then all these values just keep increasing by 1. What it says is that to get from t to the empty string, I have to delete one letter. To get from ct to the empty string, I have to delete two letters, right? I'm going from bisect to secret. Bisect is my starting string, secret is my second string. So these correspond to the number of deletes I have to do if my target is to take the empty string which comes after secret is exhausted, right? So therefore, if I have the entire first string bisect, then I have to delete 6 characters to get from bisect to secret. So that's the last column. What about the next column? Well, we just follow the same thing, right? So we see that if I have t in the second word, but I have an empty string in the first word, then I must insert the t to get there. So I have 1 here, right? So this was actually the other boundary. So this will actually 0, 1, 2, 3, 4, 5, 6, symmetric to that column. On the other hand, what happens here, right? So here we have that t is equal to t. So that means that this is the case where ai is equal to bj. So we don't have any cost at this point, and then we look and we add the cost going down and right. So 0 plus 0 is 0. So there is no edit cost for replacing t by t or matching t to t. But if I am at ct, right, then I am in the situation where I have ct on the first string and I have t on the second string. Right. So now I have multiple things I can do. So one thing is I can go to t and t by deleting this, or I can insert the t and go to tct and t. Right. So it turns out that obviously this is a better choice. So what I have to do is I have to take the minimum of these and add 1. So the minimum of these is 0, right. So what this is saying is really that this case, which I get by deleting the C, is actually the good case, because it leaves me with an edit distance of 0, and I add 1 and I get 1. So we are just following the recurrence, we are not doing anything special, right. So in every case we can just do that. I mean, this is just to explain what's going on, but you can just do it blindly. You don't have to look at the actual operation you're doing. So for instance, if I take this value, right, it will say that this is a T and this is an S, right. So since this is an S and this is a T, and it is not equal, I must take 1 plus the minimum of my neighbors. So I look at the neighbors, right. So my neighbor values are 2, 3, 4, so the minimum of that is 2, I add 1 and I get 3, right. So it's a completely local blind arithmetic operation depending on the ui and the vj that correspond to this position. So you don't have to analyze why it is happening, okay. But it will be the case in general that if you pick up the value from the bottom, right, it's because of the delete. If you pick up the value from the right, it's because of the insert, right. When you pick up a value from the right, then the I position doesn't change, but the j position changes, right. And when you pick up the value from the bottom, the I position changes and the j position doesn't change, and so on, right. So that's how we do this, and then we just keep doing this, right. So for every place you can just see this. So for instance, here again, if you look at this, so this is an E and an E, right. So then if it's an E and an E, then the edit distance should be, so why is that 2? That should be 1 actually, sorry, because it should be the minimum, it should be this plus this, right. So this should be a 1, so I'll fix that. But anyway, so you can take any position and then check it. For instance, if you take an I and an E, then it is the minimum of this plus 1, right. So you keep computing column by column, and finally you find at this position it says that if I take the entire string bisect and the entire string secret, then I have to make 4 edits. Then this is compatible with what we know, right. You have to either delete 2 letters from both strings, or equivalently delete 2 letters from bisect and insert 2 letters to make it secret. Now how do we recover that solution? Well, as before, we can trace the path of how each entry in our table was made, right. So this 4 came as the minimum, because this is an S and a B, this 4 came as the minimum of 3, 4, 5 plus 1. So we can say that this came from here. Similarly, this is an I and an S, so this 3 came as the minimum of here to here. Now this is an S and an S, so this must have come because it is equal to the diagonal entry, so this came from here. So in this way we can trace down for each entry starting from the top left. The final edit distance is the value at 0, 0. So we can trace down all the entries as they were populated depending on which of the values I picked whenever I took the inductive definition, and that's the yellow line. Now when we did LCS, right, the important things for us were when the longest common subsequence was extended, and that happened in the diagonal. But here for us in the diagonal corresponds to no edits, right. That's when AI is equal to Bj and we directly skip over to AI plus 1, Bj plus 1. So we are not interested in the diagonals, we are interested in the verticals and the horizontals. And the diagonal, yes, if it is a substitution, but in this particular example there is no substitution, so that doesn't matter. So here for instance, if we look at this first move, right, so this first move corresponds to a deletion, right. So deletion is when I remove the first letter, so I increments to I plus 1, so I go to the next row and j remains the same. Similarly, this one is again a deletion, right, so I am deleting the I. Now I am doing nothing until I come here, and at this point where I am at this particular thing, I move right, and this corresponds to an insertion because I am keeping j fixed, but I am increasing, I'm keeping I fixed, but I am increasing j. That means I am taking the first value in the second string and inserting it and then deleting the two together. So I am actually inserting this r, and then in the next step I again insert an e, right. So by looking at the positions where changes happen, if you see why each entry was added to this table, you can then recover what is the corresponding operation that added that entry, because each entry has a unique meaning, right, a horizontal line, a vertical line. The diagonal has 2 meanings, but you can check that depending on whether the 2 values are equal or not. So this says you delete a B, delete an I, insert an R and insert an E. So the code for this is very straightforward as before. So you take 2 strings, right, you get their lengths and set up this array of zeros, right. Now the difference between this and the LCS and the LCW is that you cannot just be happy with the zeros for the boundary, because the boundaries are not 0. So this is just setting up those 2 columns to go from 0 to n minus 1, right. And once you have done that, then the rest is just the inductive thing. For every position in your thing, you just look at the case is if ui is equal to vj, then you just copy the value from I plus 1 j plus 1. Otherwise, you look at the 3 neighbors, take the minimum and add 1, right. So in most dynamic programming things where you are doing row by row, column by column, the actual calculation is a very simple nested loop. So the main thing is to get the recurrence right. You have to get the inductive definition right, and once you get the inductive definition right and the base case right, everything will fall out. So the coding is very simple. What about the complexity? Well, the complexity is also the same as the other ones, because we are filling up a table of size order mn, because it's m plus 1 into n plus 1, and using dynamic programming as we have done here, but also if you use memoization, you will end up adding each entry with a constant amount of work, right. So therefore, if I take a constant amount of time to do mn operations, so the overall thing is order m times n.